Okay. So our next speaker, and our speaker before lunch, is John Ladbrook from Ford. And John, as I think he'll explain, has been doing witness models for a long time. Nearly as long as me, or a similar length, maybe we're about level. But John's going to be talking about how that use of witness has progressed in Ford, and particularly up to the HPC, which was mentioned earlier on. So thank you, John.
Good morning, everyone. I've worked for Ford for many years, and in terms of simulation modelling, what we do is we model the manufacturing facilities for engine lines, including block, head, crankshaft and engine assembly, and the material movement of parts to those particular lines. Why do we do this? Well, we do it to ensure that we meet our planned objectives in terms of cost and efficiency. So before that we launch our lines, that we achieve what we set out to achieve. And I think what you'll find with this presentation, in common with previous presentations, there are many parallels in terms of what's been said. So this is my view of what I've done over the last number of years to achieve a success in simulation. In the beginning, there was a mainframe simulation, which I had very little input into it. And then, for those of you not old enough, came the PC. It came into the department, and I got involved with simulation. And in this case, it was interactive, the models I built on the PC. And then we discovered CY, as mentioned earlier, developed up the road at Warwick University, and first used on the Metro paint shop. So we looked at it from our point of view at Ford, and we were guided to use simulation to support all our major investment programs. And since that day, we have done that basically. We've supported virtually every program that we've worked on. So that's how I've worked my career about this. In order to achieve successful simulation, we've looked at using a set of tools. The first one, and one of my strong beliefs, is that to get simulation into the hands of the manufacturing engineer and to get them dealing directly with the engineers involved in planning and developing these lines, and not only the engineers, the management as well. So in 1984, we developed a program called Mentor, which was a machine line tool. Then we had Witness come along, first release of Witness. 1987, we started using that. In 1998, we developed a tool along with one of the Lanner consultants, which was fast interactive replacement simulation tool. It was a high-level tool that helped us to develop and run models very quickly. My claim at the time was I could build a model with half an hour, given the data, of course, because that takes a long time to get hold of. And having got that, I could run my model within an hour. So I could get my results out and I could answer questions. This we run with for about 10 years. It became very successful. During that success, we developed another tool for engine assembly. Basically, the tools are spreadsheets that allowed us to capture the data. And with that capture of data, we could then transfer the data to a witness model, or in the case of first, actually build the model and run the model, because with that, there was no display. It's one of the few things that we didn't use. It was basically, I think as James alluded to earlier, it was a spreadsheet and the results come back to the spreadsheet. There were dangers to it, but we were delivering simulation, we were answering questions for the management and having an input into the planning process, which is one of the most important things. We then developed the simulation, the assembly simulation tool, along with Andy Emerson, who's not here today, but he laid the foundation of that. That built us the model. We then adapted that thank goodness our process people changed the processes so that the blocks and heads went round on a platen as well as the engine assemblies. So we were able to use the same tool, and commonising the tool has been one of the things that has helped us again deliver simulation very rapidly, because we have one tool. We only needed to develop and support one tool. We're now working on something that we call Faster, which is a collaboration we're running with Lanner currently, and we're evaluating Zimba to see what improvements we can get. So along the way I've had a lot of support from universities. It's helped me with workload and helped me with research and development in developing these tools. So, just touched on fundamentals of success. Easy to build, easy to run models with the ability to quickly deliver results. Another key, ready access to the software. Software used to come as standalone licenses with a dongle plugged into the back of your machine. That limits what we can do with them, especially as a global company. We couldn't share them at the time across the company, and so they were limited. Licenses also got lost, left in people's desks, which was not particularly good. Provide a set of tools with standardised inputs and outputs to provide improved validation of models. Having standard inputs helps me greatly in supervising people, because I can see the boxes that they've missed. Reuse of models or modules, which touched on earlier. A lot of our work is based on a set of modules that we continually reuse. We do develop them, but they are continually reused, so it gives us a trust in what we're using in terms of the underlying logic. It also allows me to reduce the skill level I need in terms of people coming in to work for me, and allows shorter learning curves, and allows non-skilled modelers to use simulation. In other words, the manufacturing engineers. I can put the tool in their hands. Key to the network license was central funding. All licenses were originally funded individually, and that was a great, despite the limited cost, was a great problem to get through finance. I don't know if other companies experience that, but lower the cost, the more difficult it is to justify. So we gave free access to a server license, and at the time we just incorporated all our licenses within the company under one banner. And we had a annual maintenance agreement in place, which, as touched on, was a previous restrictive factor. Certainly in the plants, they would cut the maintenance cost, and therefore the software wasn't up to date. So this was 1999. We had about 14 users. This is where we globalised, and we see that in doing this we're able to maximise the usage. We grew the users, but also we were able to capitalise on the network licenses, and at various times went above the total licenses that we had. So we standardised on the software, still being discussed by some of my American colleagues. We had a global network, and we met peak demands. We exploited time zone differences, which is very important, and enabled the sharing of that licenses. One of the other keys, and it's again been touched on this morning, is a standard set of tools. This is one of my input sheets. Down the left-hand side of this spreadsheet, you'll see there are the processes. That identifies the process. Each of these different colour boxes relates to a module. So we have a manual operation here, this light green, and then we have an automatic operation, the darker green. These relate to different modules, and we have a set of about 20 modules. So we make our inputs in terms of cycle time, breakdowns, etc. From this sheet. and then that will go away and will, through our witness model, loading up the data, we'll be able to build our model. Other standard tools we have, and we have about 5 tools. One is for analysing the breakdown data. One of the key inputs to our models is capturing this data. We have live monitoring systems. Manually, it used to take a long time to capture this data, sort this data. Through a research project with Southampton, we developed a tool, and we not only capture the data, create the distributions which get read directly into our model, we also able to publish data to our process team to show them where the faults are, what the fault codes are, etc. And then we come on to one of our other tools, which is the experimentation generator. There's been a lot of talk about experimentation this morning. The model building, yeah, it's important, but what is important is delivering the results. And to get the results, you need to do experimentation. So we developed this command generator, which allowed us to build many different experiments through this one tool. On here, we have the model that we're going to load up. A simulation, we save simulation, so we load the simulation up. We have a file name that we can create, and then we identify the run times, etc. So we can queue up a large number of models within here to run the experiments on. We can change varying parameters. We have a number of variables within our model that will allow us to change. So we can turn off breakdowns, turn off setup, turn off quality issues, and turn off the labour. And then we can run for various areas of the model. We can either run it by individual areas of that model or by the overall model. We find running it individually, we're able to identify the bottleneck, and then from that detail, it helps us drive forward in improving the throughput. So that's our command generator. What that does is generates a witness command file, witness command language file, which will execute the models. I don't know if everyone's used them, but basically I would say it's a macro. You can load up the command file, it will restore the model, it will look at the detail, determine the warm-up period in this case, here, and then having done that, we then set various flags, variables that are in the model to turn on the cycle time. In this case, that's on. The breakdowns are on, but the quality and operator stoppages are off. And then, again, we have setup on. So that's the experiment I'm running with this. And we then create files, report files, that we will analyse in another tool, which is our results analysis tool, based on reading information in from this file that we collect, and then we store that file, and then we run it. And then it will close witness at the end. So that's the way that we use the witness command language. It's something that I used in my early part of my career, and I found it very useful in terms of generating these experiments and getting, if you like, artificial intelligence in the hands of engineers to run models for a simple interface. Originally, we used to walk round the PCs, loading up the experiments. Took a long time, as this little slide is going to take. Very time consuming. You had to do it out of hours after people had gone home, so you could get onto their PCs, log on, etc. So that's the way that we used to run experiments. Then along came what we call the farming process, which we developed in-house, which allowed us through a central network to link the various PCs. Again, the downside was people didn't always leave their PC on, so not all our experiments run. But the other thing that was not liked, certainly by our IT people when we tried to expand this process, is the linking into the IP address of the PCs around the company, and they felt this was a very dangerous thing to do. So they stopped us doing that, and we had to come up with another solution, or they had to come up with an alternative for me. And that alternative was high-powered computing. This is something that we developed last year. They gave us 40 processors over and above what we had on a high-powered computing system in Detroit, and we adapted our command generator to link up with this. So we were then able to run our experimentation. That sounds easy, but it took a lot of work as a tripartite development between my simulation team, between IT and Ford, and a great deal of input from the Lanner team in terms of Jeremy, who really helped us along with this, and it's been a really good collaboration, and it's shown to be a really good success. So thanks for that, Jeremy, if you're here. I believe you are. So we were able to use this, and originally our current license pool is 50 licenses, and these are all user licenses. We upset a lot of other people in Ford when we first started running our experiments, because we were using all the licenses. And we were getting complaints that, oh, I can't run my stuff. So what we did is we purchased 30 additional run-only licenses, which are specifically for HPC. And then basically, although we have 40 on the HPC, we're able to use these run-only licenses. So that's been very beneficial to us in those terms. I talked about the results. They come out in standard formats, and these are some of our standard formats. This is our result collector, and one of my guys has developed this for us. It collects basically the report files from witness, and it loads them up into the tool, and through various menu buttons, and he's developed his own ribbons at the top, which hopefully we certainly find easy to use. There is a person in this room who could qualify that, but or not, as the case may be. But from these we can download various data, and these are some examples of reports. This, sorry, should leave that alone. The middle one here determines our run length within a tolerance. This is looking at buffer sizes. This is one that you'll see this afternoon, so I'll comment no more on that. I'll leave that till later. And this one is one of my favourite charts in terms of helping to sell the model. If we go back 3 or 4 years, we just used to justify the model's good by looking at the average output. And the average output, 50 jobs an hour, equal against an actual of 47, 48 is good. We now not only look at the average output, but we look at the profile of that output. So this chart, lower right here, is looking at the model, the actual. So the red line is potentially the actual, and the blue line is the model. And from that, we compare the output and the profile, and they need to be correct. But this, as a standard output in terms of selling the model, certainly to production or my own management, is an absolute godsend. It has saved me hours and hours of work and the pain of selling something to someone else, because so they can see that both the actual and the profile are the same. And then below that, we do a statistical test to tell our modelers that it's either the same statistically or it's different. So again, getting knowledge into the hands of the manufacturing engineers, and it has been very important. We also use that for comparing different alternatives as well. So that has been very important. We also get other charts out, such as bar charts, normal, busy, blocked and starved, and output, etc. So simulation approach is a standard set of tools. They are based on a central drive where they're all accessible in terms of the models. So we have in the centre that shared drive. All my models are stored on there. So not only can we get them in terms of developing new models, but those models reside there for people in the plants to then use them subsequently and take them on to look at process improvements on those various lines. So that's the overall view that we have there. So what's it done for us? Last year we run 125,000 hours of experimentation, and I know there's no way that I could do this sat on the 10 to 12 PCs that my team have. We just wouldn't have had the capacity. It's at one night we run over 200 experiments, and also the other week we run fully loaded, and this is due to someone in this room running many experiments before he left me, that it was loaded all weekend. It just couldn't have been done. I would have needed to increase the number of people in my team, needed to increase the PCs, and we don't have that room in our office, so it couldn't have been done. We've had to find somewhere else in the building. So also, and without the command generator, it would have proved impossible to run that many experiments. So through last year, the two charts below, the 125,000 hours, show the number of users that we had within the company. The red line is the total number of users, so within the company we're now at 35 users, and this tracks it month by month, so the team that run the HPC are able to identify the use of each person. Helps me to identify who's working and not working, because I judge their workload by the number of experiments they run. So it's a very useful report. And the chart on the right shows the overall utilisation for 2013, where at one point for the total 80 licences, we were up to 40%. And that's from the adjusted at the beginning of the year, which is, I've adjusted this for all 80 licences, where we're running at 10%. So HPC has shown a significant increase in the number of experiments that we run. Is it just experiments we're running? No, it is not. We have, some of them maybe, but it's given us a better quality of result and enabled us to do a lot more work in terms of evaluating various options. We're able to respond to our customers in terms of their questions a lot quicker. So, yeah, we've used simulation for over 25 years. Thank you for ever put that in. That gives me a few years. It is a part of the engineering process. Engineers come to us constantly now to ask questions. Success has driven success, and we're driving more success. And that is a problem to me. But HPC has been an absolute benefit in terms of helping us to deliver that. So, and the standard tools allows me to get people in, get them trained and up to speed very quickly in terms of running and developing models. Okay. Oh, we've gone for lunch. So that means no questions. Any questions?